reinforcement learning. The interesting thing about Q-learning is I sort of motivated this here just to avoid having to compute this after I'm done. After I got the full values, after I got the optimal values, I still have to do this step to convert the value function into policy. So I felt as if that's too painful, so instead I'll just keep track of Q. But think about the following crazy situation. Somehow I came and gave you V star. Just I'm the richest uncle you could ever have. I just gave you V star. You know now you have the V star. You just need to know what's the best action to do. Can you convert it into the policy? To do conversion into the policy, you would need these numbers. You need to know what is the action going to do in each state. And this actually, in reinforcement learning terminology, this one is called a transition model. If you do have the model, you can convert value into policy. If you have the model, you can convert value into policy. What you have, you don't count. I always had model because that's the way the MDPs are specified. But it turns out we'll see that in reinforcement learning, in fact, many of the approaches that work, they work by directly learning the value without ever knowing the model. It turns out there are two ways of solving the problems. One is you understand the model of the actions. The other is just you directly understand the optimal value. In either case, you can get the optimal policy. One is called model-based learning. The other is called model-free learning. If you are doing model-free learning and you don't have model, then if I give you V star, that's like giving stuff that I don't have hands to pick up and eat. You're giving me a nice candy, but I don't know how to eat it because I have no hands. So I've been given the V star, but I don't know how to convert it into 5 star. But instead of V star, if I track, if your rich uncle list of V star gave you Q values, which is only 4 times bigger, and which is only 8 times bigger than the amount of information they are giving. Then you're done. You can convert it into policy. Okay? So here this is just a side curiosity, but when you go to reinforcement learning, in model-free learning, there is only one way of converting the value to policy, which is if you actually track the value function in terms of Q values rather than V values. Okay? The last thing that I want to say for today before we go away is the policy iteration. And so you have the policy evaluation. I want to just give you the idea of policy iteration. There are clearly only A power S policies. There is already a brute force approach for policy-based computing optimal policy by comparing each one of them to other. Right? But here is a better idea, which is start with some random policy pi. Start with some random policy pi. Okay? And then, so basically what does policy mean? For each state, you pick an action arbitrarily. So that will be a random policy. Then I convert, now I have a nice big loop here. I convert pi to V pi. If you are doing a policy, whatever the policy, even if it's a random policy, it corresponds to a particular value function per state. You see what I'm saying? Okay, so you compute V pi. Having computed V pi, then I pull some rule because after all it's the end of the class, this is the time for magic. Then I just say, since you went from pi to V pi, now from V pi to go to pi, except V pi dash. So after I computed the value, you can convert the value to policy. You know that, right? So the value to policy would be converted, value to policy will be converted this way. Given a value, the greedy policy for that value would be a pi. One of the beauties is, and you should do this to get a sense of it. One of the beauties is if you start with a pi and you evaluate v pi and you compute the greedy policy with respect to that v. If you get the same policy back, you say, Mom, I'm done. The one that I started randomly with is actually the optimal policy. If not, this new policy will be the next iteration policy. Do this again. Sufficiently confused? Right. So it's again, the question is not what to do. What to do is quite obvious. Why is this working? It looks as if I'm sort of doing some circular reasoning. Okay? The interesting thing is the policy corresponding, the greedy policy corresponding to a value function might be different from, so here multiple different policies can give rise to the same value function. So optimal value function is unique for any problem. Optimal policy is not unique. It's like optimal distance to the goal is unique, but the optimal solution is different. It can be multiple solutions which give the same optimal distance, right? Similarly, optimal policy, so the policy can be non-unique, while value is unique. So in general, given any value function, there's a whole bunch of pi's which will give you this value function. You're picking the greedy pi among them. That will take you into the next guy's value. And then you take the greedy guy in that next guy's value. That's what you're doing. And in fact, you can prove that this is, of course, going to be, in fact, people can actually show that this has closer to polynomial complexity in terms of the number of policies that you have to play. And what is crazier is this will work even if you don't actually evaluate v pi. To evaluate v pi, by the way, I told you you have to solve the set of linear equations. The guys doing value iteration just do updates. Why am I supposed to solve equations when people doing the harder problem just do updates one by one? Well, it turns out you can do value computation also as a value iteration, as an update, without the max. So in addition, basically what you'll wind up doing is, instead of this being equal, you set this as an update. And you set basically v pi of s is some numbers to begin with, initialize it, and you keep updating every time. These updates are cheaper because there is no max operation involved. And this too is guaranteed to solve the linear equations. Okay? Now if I set this, then I will say that in fact, and this is a very last thing I'm going to say here, is instead of actually evaluating v pi completely, just do a couple of iterations of that type I said, which sort of makes the value slightly better. It's a slightly better approximation to the v pi's value. And then you do the next policy. It will still work. Full matching. Okay? Think about this. Next class we'll talk a little more about this, but mostly going to reinforcement learning, which I sort of started.
Good. Towards the listening and the recording. So it won't test